Oh, hey, didn't see you there. Sorry, I was just finishing up an experiment. But welcome to the newest episode of Matt the P-Chem guy. Today we'll be talking about LEDs, band gaps, and their materials. So let's get right into it. All right, today we will be filling some band gaps in LED theory and design knowledge. Here's a brief outline of everything that we'll be covering today in this video. Despite the recent trend of teenagers and college students to line every part of their room with these kind of lights, light-emitting diodes, or LEDs, have a vast number of uses aside from TikTok purposes. From medical devices to this lamp to the computer that you guys are watching me on, LEDs have a vast number of uses. All of these uses are based on physical chemistry principles that will be explored in this lab. LEDs are semiconductors that utilize electronic bands to conduct electricity and the free electrons within those bands. As Figure 1 highlights, when multiple metal atoms are bonded together to a very large amount, the orbital overlap causes electronic energy levels to converge and create two electronic bands, a conduction band and a valence band. As the conduction band gets populated with electrons, a current can flow. Thus, we see as band gap increases, the electron population decreases in the conduction band and conductivity decreases. For semiconductors, there is covalent bonding, and the bonding and anti-bonding molecular orbitals create distance between the two bands. Because materials like pure silicon aren't good conductors, other elements are added in a process called doping. When we add an element from the 3A group, we get a p-type semiconductor, and when we add an element from the Fa group, we get an n-type semiconductor. Figure 3 shows the different effects of p and n dopants. N-type dopants have an extra electron and thus form a new dopant band below the conduction band. For p-type dopants, they have one less electron and create a dopant band just above the valence band. For both of these, it makes it easier to excite electrons at lower temperatures. When electrons in the conduction band decay down to the valence band, they release energy in the visible spectrum. Modern LEDs use double heterojunctions, as shown in Figure 4. That separates the diode into three sections. This structure forces electron carriers, which is the field circles, to collect in the active semiconductor region and then decay through recombination to produce light. As Figure 4 shows, the active band gap energy difference is proportional to the energy and wavelength of light emitted. By quantitatively comparing the two band gaps, we can see how dopants improve LED efficiency because the active band gap should be smaller than the intrinsic one. Thus, in this experiment, the main objective is to understand how band gap and electronic band principles play out in LEDs. The main question is what the band gap values for each LED are and what the dopant ratios are. One hypothesis for this experiment is that for the red, orange, and yellow LEDs that use aluminum and gallium, we predict that as the ratio of aluminum to gallium decreases, the active band gap will decrease as well, and the conductivity will increase. The other hypothesis is that the silicon standard diode will have a poor conductivity due to no dopants being added. Because of this, the population of electrons in the conduction band should be very low. Why this all matters is that this experiment and topic will provide undergraduates with useful insight into technology that powers all aspects of our lives. It also highlights how understanding physical chemistry theory can allow and inform researchers and manufacturers to increase the practicality and efficiency of products. The first part of the investigation involved a setup as seen in Figure 5, where a beaker of water sits on a hot plate with a stir bar inside, and the LED connected to the circuit and the temperature probe are sealed off in a test tube and immersed in the bath. The Vernier Logger Pro computer software was used and set up as shown in Figure 6, where two graphs are simultaneously displayed, measuring potential with respect to temperature and time. We can use the simplified equations shown to calculate the band gap if we know the voltage and the temperature. In this equation, Q is the charge of an electron, V is the potential or voltage, and T is the temperature. Thus, by using the Logger data to create a QV over T versus 1 over T plot, the slope of the linear regression should be equal to the intrinsic band gap. The second part of the investigation involves calculating the active band gap and dopant ratios. Using an ocean optics UV-vis spectrometer, as Figure 7 shows, the fiber optic cable was held next to the LED when fully lit, and the emission wavelength was obtained for all 5 colored LEDs. Figure 8 shows the individual emission spectrum for the orange LED. Using the wavelengths of max emission, the active band gap energy could be calculated using the simple E equals hc over lambda equation. The active band gap could then be used to calculate the dopant ratios. For the red, orange, and yellow LEDs, the dopant used was an aluminum gallium indium phosphorus diode. And for the green and blue LEDs, it was an indium gallium nitrogen diode. Based on the formula shown from the literature, the ratios of dopants could be determined by solving for X. First, let's look at the results for the intrinsic band gaps. Figure 9 shows all 5 colored LEDs and a silicon standard on a QV over T versus 1 over T graph. This graph was used to calculate a line of best fit and error for the linear regression, and thus Table 1 was created with the intrinsic band gaps in coulombs with error. Next, we have the results for the active band gaps from the UV-Vis emission spectrum. Figure 10 shows the normalized emission peaks for each LED with peak wavelengths and full-length half-maximum points labeled. The values for each are presented in Table 2. The full-length half-maximum values give a rough estimate of the resolution of each peak, with green having a significantly wider peak than the rest. In Table 3, we have the active and intrinsic band gap values in electron volts for each LED. As expected, the active band gap for each colored LED is smaller than the intrinsic band gap due to the effects of dopants. Additionally, for both band gap types, as wavelength decreases, the energy increases. Using the active band gaps, I was able to determine the ratio of each element in each diode. The relationship between these values and the corresponding band gaps will be further analyzed in the discussion portion. The final results regarded the silicon diode standard and quantitatively assessing how good of a conductor it is. Thus, using the formula shown, the population ratio between the two bands was calculated at room temperature based on the intrinsic band gap energy represented by delta E. The K constant is the Boltzmann constant. With a population ratio of 1.5 times 10 to the negative 21, the silicon diode is a very poor conductor at room temperature. All right, time to get a little serious. Now, what exactly do those results mean? The experimental results match well with the theory that due to dopants and the heterojunction structure, the active band gap should be smaller in magnitude compared to the intrinsic band gap. While most of the LEDs have similar differences between the two band gaps, the green LED had an abnormally large intrinsic band gap value compared to the rest. The source of this error could be due to the data collection process. For example, if data was collected at a rate greater than 5 degrees per minute, this would not have allowed the temperature to equilibrate across the LED and the temperature probe properly, thus potentially causing a larger value seen. Looking more closely at the identity of the dopants and their effects on the experimental band gaps, for the red, orange, and yellow LEDs, the data shows that as the amount of aluminum increases and gallium decreases, the band gap increases, which means that the conductivity decreases. Because aluminum is a third row element while gallium is a fourth row element, gallium should have a larger radius and thus its valence electron should be more loosely held due to having a smaller effective nuclear charge, which would ultimately make gallium more conductive. This theory is supported by the data because the red LED, which had the most amount of gallium, had the smallest band gaps, which would mean the greatest conductance. The same theory supports the trend for the green and blue LEDs. Thus, it can be concluded that elements with larger radii and lower effective nuclear charge are better at decreasing the active band gap and making a semiconductor more conductive. Looking back at P and N junction diodes, it may be wondered by students why for N-type semiconductors, even though the valence band is lower in energy than the dopant band, electrons don't really decay to the valence band. This is due to the fact that the electrons in the conduction bands are from the dopant, whereas the large band gap between the valence and conduction bands make it harder for more electrons to transition to the top band. This causes the conduction band to have less electrons, which means there will be less electrons decaying into the dopant band and even less decaying into the valence band. Looking back at the UV-Vis emission peaks, while most were similar in width, the green peak had a significantly larger width. There are multiple potential explanations for this, but the most likely one is thermal broadening, which is caused by atoms having faster movement due to increased temperature. Let's now revisit the original hypotheses made. The first hypothesis was supported by the data because the trend for the red, orange, and yellow LEDs was that as the amount of gallium increased, the band gap decreased, which means greater conductivity. And this corresponds to periodic trends and electron band theory. For the prediction of the silicon diode, this was confirmed through the calculation of the population ratio between the conduction band and the valence band, which was shown to be incredibly low and well below the 1/3 threshold. To make this diode into a good conductor, there are two alterations that can be made. We could either add P and N dopants to create an active band gap, or we could increase the temperature by a significant amount, as shown in the formula. Given the current intrinsic band gap energy, when the temperature is at 15,000 Kelvin, we get a ratio of 0.39, which would make it a good conductor. However, there is no practicality to this, as that is incredibly high temperature, and thus a better option would be to add dopants that decrease the band gap. This experiment incorporated many beneficial and educational aspects for P-Chem students. The method and procedure were easy and safe to follow, and in the process of doing the calculations, there was a clear connection between the electron band and dopant theories and the results. Additionally, to emphasize the cross-disciplinary nature of LEDs in research, collaboration with chemical engineer students could be done to actually create diodes and then test the efficiency of them and measure the band gaps for those as well. But that's all the time we have for today's episode of Matt on the PChem Guy. So I will see you guys next time.